So I applied for a computer science high school. And it turned out very early that I was not going to become a computer hacker. But my teachers encouraged me, because I was very good at math, that I would apply for a program that was aimed at higher education. So I did that, and during my high school years, I also interned. One internship I had was at SKF, which is the bearing company. And I got that internship because I wrote in my application that I like working with Excel. So that's, if you never know what stands out. And then when I finished high school, I had a summer job at the Volvo car factory. And I used to mount the lights of the cars and tune the axis for the wheel. And it was a very good summer job, but it also made me realize that I wanted to study and work hard. So I applied for Chalmers University, and I chose to apply for engineering physics. And the reason was that in the booklet that they gave us, it said that this was the least practical program. And I thought, coming from computer science and electrical engineering, everything practical could go wrong. So if it's pure theory, I imagined that it would be much more simpler. So I got in Chalmers University, and I was so happy. I thought, well, this was the hardest part. It was to get into university. And I did not succeed my first year. I failed 6 out of 8 classes. And I was very upset, and I thought, okay, what should I do now? But I decided I really like physics. I'm going to work hard. And then my second year at university, I worked hard, but I joined a lot of student organizations. And again, I failed most of my classes. But at the end of my second year, I did an internship at Volvo Cars, and this time at the office with engineers. And I had a supervisor over there who told me two things in life. He said, first, you cannot live at home the rest of your life because you're going to become a wuss. And the second thing he told me, that if you want to travel, you should do it now because you're not going to have more time later in life. So, and I remember I always wanted to travel, so I decided that I wanted to join international programs to study abroad. So my third year, I worked very hard. I studied 150%. I brought up all my classes and all my grades. And the first thing that paid off was that I got my internship at Cornell as a research assistant. And that was the first time I visited the US. And then directly after that summer, I got into the Erasmus Mundus program, which was a joint master's. And the first year was in Belgium, at Catholic University of Leuven, where we studied nanoscience and nanotechnology. And by doing so, I then came back and did my second year at Chalmers University. And I I did a master thesis on micro machine gap waveguides. So for those of you who went to Sadia's talk, you might know a little bit about what gap waveguides are. So life is funny, because one of the classes that I failed in my second year was electromagnetic field theory. And then what happened was that with my master thesis, I got a PhD working with high frequency gap waveguides. So life is funny, because I remember I failed the class, I worked hard to pass it, and I thought, I'm never going to use this ever again. And you never know what skills you'll actually need in life. So I did my PhD at Chalmers University, and I graduated in December 2016, and I was thinking about my next step. So my boyfriend at the time, now husband, was very keen on California. So I contacted professors and research facilities all over California. And I didn't get any replies. And then I remembered that a friend of mine that I met at a conference gave me a contact at JPL. So I contacted Theodore Reck at JPL, and he answered. And we had a Skype conversation, and we decided to write a postdoc proposal for the Wenner-Gren Foundation. So at this time, I was at a conference in Las Vegas in January 2017, and the proposal was due the end of the week. So I basically went to the conference in the day, and I wrote the proposal in the evening. But it turned out well, because I got the Wenner-Gren Fellow, and then I moved to Pasadena. So Pasadena is a city outside of Los Angeles, and it's the home of the Big Bang Theory, Caltech, and of course the Jet Propulsion Laboratory. So in October 2017, I started my postdoc over there. and I had no idea what awaited me. So for those of you that don't know anything about JPL, JPL stands for the Jet Propulsion Laboratory, and it's a federally funded research center. It's one out of 10 NASA centers in the US, and it's managed by California Institute of Technology. Its core competence lies in unprecedented robotic space missions, and JPL has sent unmanned missions to every planet in our solar system. And their history is actually quite fun. In 1936, around Halloween, 5 students from Caltech and 3 enthusiasts went up the hills and tried to launch a rocket. And they did several tries and they didn't succeed, and they came back 2 days later. And on the 5th try, they managed to launch the rocket. And this is actually what jump-started the space age in the US. And then I think about 20 years later, the first rocket to orbit the Earth and then safely come back was launched. And right after that, JPL joined NASA. So JPL was founded before NASA, actually. JPL also has a history of women in technology, if you want to call it that. So back in the 50s, a lot of women was working as human computers. So back then, when computers were, as we know it, were not used, a lot of women were hired to do math by hand. So this was a skill that was considered being more of a secretary level, and they had to do all the calculations for the project. And times weren't perfect. They had a beauty contest called Misguided Missile, but these women were a very important role with the space competition that happened in the 50s and the 60s. So by being a part of this, JPL opened up a lot of upper position for women, and these women paved the way for people like us. So this is a picture actually from JPL maybe 2 years ago, where everyone was gathered, all the women at JPL were gathered for a group picture. And as you can see, times has changed and the atmosphere is getting better. So that was a little bit about how I ended up at JPL, and now I'm going to talk about what I'm actually doing at JPL. So, of course, this is not a one-man job. There's a great group of people working on all of these projects, and the names are Subhash Kanal, Sven van Berkel, Maria Alonso del Pino, Theodor Reck, Cecilian Kubiak, Mina Rezade, and Gautam Chattopadhyay. And as I said before, the title of my talk is going to be Silicon RF MEMS for Terahertz space applications. So a lot of you probably recognize this. This is just an image of the spectra. And at the lower frequencies, we have radio, and at the upper frequencies, we have X-rays. And the place where I'm working is the terahertz gap. And what kind of applications do we do at JPL with terahertz? Well, I used to be in a group called Submillimeter Wave Advanced Technology, and they worked a lot with terahertz projects. And for different sciences, for example, for astrophysics, it's important to study the galaxy that we're at. So we send up balloons that can receive signals that we can't really receive here on Earth due to our atmosphere. And these projects are used to gather information to understand how our galaxy was formed. But Earth science is also a big thing. So JPL also studies the climate on Earth, the ozone depletion. And one good example is MLS, which stands for Microwave Limb Sounder, where it monitors the temperature changes in the edge of our atmosphere, so the limb of our atmosphere. Another applications are planetary science, so to study planets and moons in our solar system. And a great project for that is the Microwave Instrument Rosetta Orbiter, MIRO, which was one of the first microwave instruments sent out into space. And MIRO was successfully able to detect water vapor of a comet. So I mentioned a word before that was MEMS, and I don't know how many of you are familiar with that, but MEMS stands for Microelectrical Mechanical System. And actually you can find MEMS in a lot of everyday things. So you can find it in smartwatches or TVs, but also if you have a smartphone and you know when you flip the screen of a smartphone, the picture follows, and this is actually a MEMS sensor that is triggered by the motion. So what advantages do we have with MEMS for space applications? Well, MEMS are very robust for vibration. So when everything we do, we need to launch them into space. And it's good that MEMS have a very low mass, which means that their resonance frequency is high. And by having a high resonance frequency means that they don't break easily for lower frequencies. They're also very robust for radiation. So a good example is if you have a semiconductor switch and it's exposed to radiation, it will probably fail very easily. But a MEMS switch will not as easily fail due to radiation. And they're also small size and lightweight. So they can enable compact, smaller instruments so honestly, a lot of space and volume is very expensive. So we don't want our system to take too much space when we launch them. And if we can make smaller systems, we can fit more systems. So are there any MEMS in space already? Well, yes. A good example here are, this is an atomic force microscope on the Phoenix mission. And this was used to feel this surface roughness of the Mars surface. So it was feeling the grain size. Because we haven't been there, no one's been there, so we don't know about it. Another example are microfilters that are used on the James Webb Telescope. And by controlling which shutters are open, we can control what part of a field of view we get light from, and then we can easily filter out certain sources. There's also biological applications. So lab on chip, they have sent up a GenSat where they actually wanted to study how bacteria would evolve under zero gravity, so in space. And then the last, and maybe the more famous one, is when InSight was launched to Mars surface, it had a little MEMS seismometer that was designed to measure Marsquake up there. So there's a lot of MEMS applications already, and it's not new, but it still hasn't established yet. So why do we want to use MEMS? Well, we want to detect water, and we want to do it by remotely studying surface on other planets or moons, or studying comets and their water vapor. And the reason why I want to look for water is water, for example, is a very good indicator of life on other planets. It's also a good resource. So for example, if we want to study a surface and need to inhabit that planet for a while, it's good to have a water resource. Water can also give us clues about how our own solar system was started. So by studying the water coming up of comets, we can get more clues on where our water came from and where it originated. So now I'm going to pull in the terahertz part of this. And as this graph here shows an atmospheric attenuation for different frequencies. And basically, the highlighted areas, as you can see here, are all frequencies for water lines. And if you look at them, the lower frequency and the higher frequency, there's almost 3 orders of magnitude difference in how strong the peak is, which means that if there is water on a surface and we are scanning it with a higher frequency, we're more probable or likely to find water than if we were looking at it with a lower frequency. So that's why we need to go up to these very high frequencies. And at the pink line here is 557 gigahertz. So how are we mapping surfaces today? Well, today mapping of surfaces is done by either physically moving the antenna or actually the whole spacecraft. So imagine if the antenna was electronically steerable. Then we could map a surface without actually moving the antenna or the spacecraft. And this would reduce mapping times, mass of the instrument, and also the power consumption of the instrument. And it will make the antenna much more compact. So here we have a sketch of the state-of-the-art system. And we have our receiver system down here. And then we have our steering mirror. And as you can see, the mirror here is 30 centimeters, and it's used to steer the direction of the beam. And it's just a mirror that's 30 centimeters. Then we have the motor underneath it and extra components. So it's quite a big system. We then also have a flip mirror. which is used to calibrate the system. So it alternates between the incoming signal and our calibration load. And the mirror of the flip mirror is about 5 centimeters, but then the motor is even bigger. So what we're proposing is to take this system and change it into a MEMS integrated receiver system that looks something like this. And that would mean that we can remove all of these parts and replace it with something that looks like this. So what requirements do we have when we work with MEMS and when we work with space applications? Well, if we want to reduce size, we need the MEMS to be in the same plane as the waveguides. So this opened up possibilities for full silicon systems, which makes it a lot easier to fabricate, but also save space in the system and reduce losses. We need to keep the actuation voltage below 100 volts so we can avoid dangerous discharge in vacuum. And for our application, we want to operate around the waterline at 557 gigahertz. And that means that we need to work with the surrounding frequency band of 500 to 750 gigahertz. So let's take a look at the system a little bit more. So up here, we have a phase array antenna. And how would we do that? Well, first of all, phase array antenna, imagine that you have an array of identical antennas, and they all send out the same signal with the same phase. They together will then create a beam going in one direction. Take the same array and then add phase shifters to each array. By doing so, we can send signals with different phase from each antenna, and therefore we can change the direction of the beam. So an example of a phase array antenna would be a stacked system like this. And the advantage would be that it's a planar technology, it won't take too much space. It will be electronically steerable if we can have phase shifters inside a feed network. However, to find continuous phase shifters operating at high frequencies, and when I say high, I mean above 300 gigahertz, they're not commercially available. So we have to make our own phase shifter. So we are making a MEMS phase shifter. And how does this MEMS phase shifter work? Well, if we start with one part of it, this part here, which is a silicon slab, basically, if we have a waveguide with an incoming electromagnetic wave, and we then insert a dielectric slab into it, we would have the higher the dielectric constant, the higher phase shift we would get. However, if you have a high permittivity, you would have a high reflection too. So we need to have it a gradient system. So we need low permittivity going to high to create the phase shift, and then low again, so to reduce reflection. Therefore, we don't want to mix a lot of different materials, so different permittivities and combining it will make the process very complicated. So what we're doing is we're taking silicon and we're perforating it with hexagonal holes. And by changing the aspect ratio between silicon and air, we can control the permittivity of the slab, the effective permittivity. So we can have everything from 11.9, which is only silicon, all the way down to 1, which is air. And then by doing different combinations, we can control the permittivity. So we took these calculations and we made a design that looks something like this, where we have a high density material in the center, which would create most of the phase shift. And then we have a low permittivity material on the edge to reduce reflection and also reduce losses. So the way that it works is when we insert the slab into our waveguide, depending on the position of the slab, we can get different phase shift. And then if we insert the slab all the way in, our simulation shows a phase shift of 177 degrees. So we did our initial simulations on only the slab itself. We got a reflection of below minus 20 dB, and then a transmission around minus 0.101 dB. However, this was only the slab. So then we had to take into account that we're going to put this in a 20 millimeter long waveguide that's made of gold. And because of that, our conduction losses would, at these frequencies, would increase the loss, and we would be down at 1.5 dB. So how do we actually move the slab in and out of the waveguide? It sounds good in theory, right? Well, this is where the MEMS part come in. So we designed a MEMS motor, and it's actually the part that you see within this white rectangle. It's something that looks like this. So we have two combs, as we call it, and a spring that's attached to one side, and then the other side is attached to one of the combs. By applying a voltage over these two combs, we can attract the fingers within the combs into the other one. And by doing so, we move the whole system. And then we can control, depending on the voltage, we can control the force. And therefore also, by knowing the spring constant of our spring, we can control how far in the comb moves, and therefore also how far we can move our slab. So moving it very far is difficult, and our waveguide width is 195 microns. So we want to move it 95 microns our waveguide is 190 microns, and we want to move it plus minus 95 microns because that's much easier to move than a total 190. So we need two motors. One motor is connected to what I call V in. So when you apply voltage over V in and ground, you would move the whole system into the waveguide. And then if you apply voltage over V out and ground, you will move the slab out of the waveguide. So depending on the voltage we apply, we have a neutral position of the slab inside the waveguide and halfway through. And depending on which one we apply, you can see that up to around 56 volts, we will move the slab either completely out or completely into the waveguide. And this is built by micromachining. So silicon micromachining is done here at the Micro Device Laboratory. And the way we do it is we have a sandwich wafer. So it's a silicon dioxide, silicon wafer. So the top silicon part is 30 microns, and that's actually the width of our silicon slab. And the bottom part is 350 microns, which is our handle layer. So the first thing we do is we pattern the top part, and then pattern our oxide that we cover with, which is a hard mask. We then flip the wafer, pattern the back side, and open up the oxide on the back. We then use these oxide masks to etch the top layer, so the 30 micron layer, which defines the hexagon pattern in the silicon slab, but also defines the fingers and the combs that move everything. We then flip it upside down and open up a big cavity behind. And by doing so, we etch all the oxide so the fingers can move freely. And this is about a 40-step process that we do in the clean room. So here we have a video of actually the slab moving when we apply a voltage. So as you can see here, by applying a voltage, we move the slab all the way into the waveguide, in and out. So it's pretty cool actually. So we're applying about from 0 to 60 volts in both directions, and this is how we control the position inside the waveguide. Okay, so we have to measure this because we built it. And then we measured a maximum phase shift of 145 degrees. And then we tried to cycle it a few times. And here it says 20, but we actually did cycle it 10 million times. And it was pretty stable up to 10 million cycles. And then when I was talking a lot about losses, because that was important too. So we measured the losses for 3 positions: a neutral position, which was the slab halfway through the waveguide, and then when it's fully inserted and when it's fully outside. And we got transmission around minus 1.5 dB and a reflection around minus 20 dB. So, but I did mention an antenna, right? So let's go into that. This is a design of our phased array antenna, a proof of concept. And if we open up the antenna, what we have here is we have our feed network where we incorporated these phase shifters that you just saw. And then each phase shifter is connected to one waveguide port. And then on the top here, we have a silicon antenna that is designed to take the different signals, and depending on the position of the phase shifters, we can have a scanning, we can decide a scanning angle of the beam. So the antennas were designed by our two postdocs, Sven van Berkel and Subhash Kanal. Both of them are so-called MPP postdoc. They're part of the NASA postdoctoral program, which you can apply for when you finish your PhD if you want. Sven has designed a leaky wave phase array antenna, which is a 3-layer silicon design, and Subhash has designed a cavity back slab phase array antenna, which is a 2-layer silicon design. Both antennas can scan up to ± 10 degrees, and the reason is because our phase shifters can only move up to 145 degrees. They are limited to how much they can scan without having too much losses. Okay. So let's talk about the next part. This is the calibration MEMS switch. So because we're working high frequencies, we cannot use switches that are used for circuit board technology. We have to use waveguide switches. And there have been a few MEMS waveguide switches produced before. And most of them need electrical or mechanical contact to block the incoming wave. So over here is one of the first MEMS waveguide switches, where it actually has these filaments that are gold and polysilicon together, and we heat them. And by heating them, they start to curve because of the difference in thermal coefficient, and then they kind of block the wave with their iris. This is another example where we have filaments that are naturally curved, and then they apply voltage pulling down these filaments, allowing the wave to pass. This work is done by a group at KTH, and it's a 500-750 gigahertz switch, where they have these little grid network, and by applying a voltage, they close the grid and make it impossible for the wave to pass through. The issue with a lot of MEMS waveguide switches, because they need mechanical electrical contact, it causes a lot of mechanical stress, stiction, lifetime issues, and also a difference in ohmic contact due to cycling. So when I was a PhD working with GAP waveguides, I got this idea to make a contactless waveguide switch. So basically, we have 3 waveguide ports. We have a receiver, antenna, and load. And then each, we have a U-bend that connects 2 of the port at a time. We then add a 10 micrometer air gap because, as I said, we want to avoid contact. And then by doing so, we might have leakage because 10 micrometers is enough for leakage. So therefore, we add this electromagnetic band gap surface. And by doing so, we can block the wave without actually having any contact. We then have a 9-degree angle between the 2 ports. And by rotating this disc, we can connect the receiver to the load or the receiver to the antenna, and so on. So initial simulations show that we have a reflection for just the switch about less than -20 dB. And then also, very importantly, we look at the isolation. So the isolation is what goes between 1 and 3 when they're not connected. And then we also looked at the transmission, which is also, we're pretty happy with that. And the simulations show 0.6 dB. Again, this is only for the switch. This is not for the whole system. So as I said, it's 9 degrees between ports, but we don't want to move that much. So we put it in a neutral position in between ports. And that way, the U-bend only has to move ±4.5 degrees. So how do we rotate this? Well, again, we're using a motor, a MEMS motor, and we're doing something similar as the phase shifter. We have a comb actuated, but this time the comb is radial comb, so it changes by radius. And then we have a little spring here, as I mentioned before, and by applying a voltage, so if we apply a voltage of V+, we can rotate the disc counterclockwise. And if we apply a voltage of V-, we can rotate it clockwise. So this one is designed to rotate up to ±5 degrees. And the whole chip will be placed in a block, something like this, with antenna, receiver, and a load. and we would actuate the device from the side here. So here, I have an animation showing actually the real fabricated switch. And when we apply a voltage to this, we can see how the switch rotates. And you might wonder, where is the waveguide? Well, the waveguide is actually on the backside of this disk. So, but I want you to look at this little bar here and the radius that we have. So by applying a voltage, you can see that is moving depending on the voltage all the way up to 5 degrees. I'm going to do that again. So look inside the red circle and you can see we're slowly increasing the voltage and we're moving all the way up to 5 degrees. And we actually have a real life film of the whole thing. So in this movie, we're applying the maximum voltage and we're just turning it on and off. So this is the off state, and then we turn it on, and this is the on state. And you can see how it goes from 0 to 5 degrees with on and off. So, well, where were we? We were talking about this. We had a system that looks like this, and we want to remove all of these components. We want to replace it with a MEMS integrated receiver system to reduce it to something that looks like this. So how far have we come? Well, as I showed you, we have the MEMS switch. We designed a MEMS phase shifter that will be implemented in a phase array antenna. And then all together, we just need to, we have all the components to make a compact, fully integrated MEMS system. So to summarize, MEMS-based receiver systems can enable rapid remote detection of water. Our fabricated MEMS phase shifter showed a total phase shift of 145 degrees at 550 gigahertz. And the MEMS phase shifter can be integrated together with the phase array antenna, and we can have a scanning angle of plus minus 10 degrees. Also, our MEMS switch was demonstrated to rotate plus minus 5 degrees. So shows that we can replace this big flip mirror with our MEMS switch in the receiver system. So to summarize this, silicon RF MEMS enables compact, lightweight, and low power integrated receiver systems. Thank you all for listening, and I will take questions now. Let's see, so I'll look in the chat box maybe.
Ma'am, you're on mute.
There is one question from S. Kanthamani. MEMS products are sellable. Just wanted to know the status of the.
Yes, there are MEMS products, but there are no phase shifters that are commercially available. So yes, there are definitely MEMS products.
There is another question from Anshika Chaturvedi. Do you have any concern about switching speed of MEMS-based components?
So not at the moment. I haven't measured the actual speed compared to simulations, but as you can see, the video that I show was in real time. So I don't think we're going to have an issue with calibrating and the switching speed of the MEMS switch.
Thank you. There is one question from Dr. S. Raghavan about BioMEMS. Present research level, he just wanted to know how far it has reached. Means what are the developments about BioMEMS?
Okay, so it depends on how you look at it. So the fun thing about working in JPL is they need one thing to work. So if you make one device that works for their application, they're very happy with it, but it might not be commercial. But there's a lot of the kits, you know, where they do home blood tests or things like this, it has a lab on chip. So there is BioMEMS that are getting pretty far. Also, I think BioMEMS, a long time ago when anthrax was an issue, They use BioMEMS devices to detect attracts on envelopes, for example. So there is BioMEMS products available. There just I don't think there are any BioMEMS for internal use yet because there's a lot of approval that needs to do for that. But there are a lot of these home testing kits involved by lab on chip.
There is one question that people say that research, just a minute. People say that research on MEMS is almost over. So you need to highlight on this aspect.
Maybe I want to rephrase that question. Please talk about the opportunities and future on MEMS research. Yeah,
Absolutely right.
So this is a funny thing, and actually, what I like about MEMS is there's so much left to do. So MEMS has not really kicked off yet, but I think the first switches came in the 80s and it never really kicked off, mostly because of what I was saying, because of stiction. But also there is all of these wearable technologies like the Apple Watch and Fitbit and all of that. That's 100% MEMS. In your smartphone, the microphone, there's humidity sensors. There's a lot of commercial MEMS out there. But what I like is MEMS is a very grateful research area because when you come up with something new, it's new because there's not a lot of people that's touched on it yet either. So I don't think it's over, but I do think that if you believe in it, you need to work on it to convince people.
Yeah, definitely. I appreciate your answer very much.
It's just started. That's my opinion.
Yeah.
The next question: what is the power handling capability of MEMS switch?
So, okay, I haven't done the math, but we're working at about 70 volts and we have high resistivity wafers. So there's not a lot of current going through. So the power handling there's not a lot of power actually for these devices. And that's normally the benefit of working with these switches.
Is MEMS require any cryo cooling? This question is from Anamia Bhattacharya.
Not the MEMS that I've been working with. It's actually the span when you work with silicon, it's very thermal stable, so you can work in a lot of different temperature ranges. So there's very few MEMS that I know that needs any thermal cooling. Although when you work with space applications, if you're on a hot planet like Venus, where the temperatures goes up to 300 C, you might want to cool because of all the electronics, but normally it's not because of the MEMS.
Yeah, Anamia Bhattacharya is my colleague from Space Application Center, which is Indian Space Research Organization, Ahmedabad. So Anamia Bhattacharya, if you are there, you can interact directly with Dr. Sofia. Yeah, that would be a direct connection between ISRO and NASA.
Thank you, sir. I will connect. And one more question is how much noise temperature you are getting by using this MEMS switch?
Wait, could you repeat that?
How much noise temperature you are achieving by using this MEMS switch? Because from the Terahertz space applications, we require this sensitivity and noise temperature. Otherwise, you cannot detect that particular spectral line about this attenuation band you have shown in the first slide. So if we see that we are getting some spectral line around 230 gigahertz for detecting the carbon molecules. So how much noise temperature you are receiving by using these CO lines?
The MEMS shouldn't affect the noise temperature too much, but it is connected to a receiver system where we have all of our diodes and things, and they are temperature sensitive and noise. But the MEMS waveguide is not.
For detector part, you are doing by using the Schottky based diode, I think, right?
Yes. So we can. The receiver system has the circuit, but the MEMS is part of the antenna and the waveguide system.
Okay. Thank you.
Thank you.
Now there is next question from Dr. Rekha Labde from Maharashtra. What is the dynamic pull in MEMS?
The dynamic pull in MEMS. Could Dr. Rekha please elaborate that question?
Dr. Rekha, can you elaborate the question?
Yeah, good morning. I'll elaborate that. So actually, I want to know what is meant by the dynamic pulling in MEMS, parallel plate electrostatic actuators? Actually, in that I want to know about the dynamic pulling.
Oh, so how, what is our failure voltage? Or
Yeah,
more about
it's maybe pull-in voltage or that kind of question queries she's
Yes.
having. I think so.
Yes, sir. Yes, sir.
Yeah.
Yes, sir.
Okay, so let me bring this up. So I went this over very quickly, but here we go. So basically, a simple way of looking at it is the pulling force is controlled by it's proportional to the pulling voltage of a voltage square, and then also we have the what dielectric is surrounding that, but it's normally air or vacuum. And then what happens is the further in you get in, the more unstable the system goes. So there is, I don't think I mentioned it, but there is a stability criteria you need to fulfill. So you can't just continuously apply how much voltage you want to go all the way and go as far as you want. And that's why we didn't design a MEMS that went 190 micron, because the stability is, since we don't want to go about 100 volts, we needed to move very far for low voltage, which means we need a very soft spring. But having a very soft spring means that the further it goes into the system, as you can see in the right picture, it's also more likely to get pulled to the side, and we have instability in that way. So there, I didn't bring the equation for it, but there is a criteria we need to fulfill both for the lateral and the perpendicular spring forces. Well, did that answer your question, or did I misunderstand?
Yeah. Thank you, madam.
Thank you.
I think we should read to the last question. Is MEMS research challenging due to the interdisciplinary aspect?
I would say yes. So my background, as you saw, was engineering physics, and then I went into nanoscience and technology. But I'm not a mechanical engineer. I know a little bit about mechanics, but that's something I had to educate myself on. And then we're working with RF applications, so you have to work with knowing a lot about, as I said, reflection and electromagnetic field theory. And the same goes for other kinds of MEMS. If you're working with BioMEMS, you need to understand a little bit about biology or fluid dynamics, for example, because you have these very tiny vessels where you want to have the fluid going. So yes, it is an interdisciplinary subject, but I think that's why it's also a lot to do, because when you mix different subjects, that's where you go to the next step, in my opinion.
Thank you, Dr. Sofia, for this wonderful talk. I would like to thank the organizers for giving me an opportunity to chair this session. I would also like to thank all the participants for their participation and patient listening and having more interaction with Dr. Sofia. They can also get connected with you through mail. And now I hand over this podium to our moderator, Ms. Gopika, for the virtual photograph session. So over to you, Gopika.
Thank you very much, Dr. Ravilasha Mishra. I just want to have a little bit of more interaction with Dr. Sofia. Not very much technical interaction, but in general, for the opportunity, especially for youngsters. So before that, I have just one little bit of technical queries, because MEMS is a very good candidate for various applications in antennas also. You have talked about phased array kind of applications, and then we have different kind of reconfigurable antennas, multifunctional antennas. So for these kind of applications, in various places, we use other solutions.